The, the speaker for the lecture 38 of RSIC 2024 will be Dr. Chaitanya Sharma. It is indeed a great pleasure to be sitting here listening to a person who excelled in the areas of non-adiabatic dynamics, low-dimensional materials, plasma-assisted catalysis, and various other interdisciplinary research themes. Eager to take in all the new information that will be shared today. Thank you.
Thank you. Okay. Am I clearly audible to you? Yes? To you? Audible? Even louder you want? Okay. Fine. Okay. So, my name is Chaitanya. So, as I told you yesterday, I think most of you are there yesterday as well. So, I work in the chemistry department. I work in the area of computational chemistry and material science. This is what the areas that we are working on. So, here are a few research areas that our group generally works on. So, there are a few more, but I am not showing you everything here. So, the first one is called as the charge transfer dynamics. Okay, what is it and where it is useful? Okay, you can just first in the beginning you listen to me, after that you can take the notes a lot. Okay, this is only one slide. I want you to listen so that you will get a grasp of what we are doing. So, the first one is charge transfer dynamics. Where do we study charge transfer dynamics? I just want it to be interactive. Charge transfer, where do you expect that there is a charge transfer? Formation of bonds. Sorry, electron? Electrolysis. Okay, there is a charge transfer, or electrolysis is about like breaking, right? Okay, so the charges, yeah, please. Electricity is the transport of the electrons, right? That's what we call as the electricity. Okay, so whatever I have shown you, the materials there, these are called as the organic donors and the acceptors. Okay, so a material, so let us see in this way. When does water flow? Okay, now there are many. Yeah, you are saying? Pressure difference, you would see air flow, right? Of course, water can also flow, but like naturally I am asking, like when you see that the water flows in the nature. So high potential to low potential whenever is there, potential or anything like you, if you are considering potential energy is high, right? When we are seeing that there is a high area means what? MGH is high there, another area that is MGH is low. So naturally water will flow from there to here, right? That's what it is. Similarly for us, when we wanted to see that electron is flowing from one side to the other side, there should be for electron related potential that is low here, that is high here. So naturally it is going from one place to the other. So the place where you have higher potential is the one that is like a donor. Like if it is a hill in your electron side, if it is water, if water is stored on the hill, it is natural for it to come down. So the hill will be the donor and the ground or the plateau will be the acceptor. Similar case here, that buckyball is the one that is the acceptor and the bottom one whatever is there, that is the donor. Don't think that this is a height wise thing, this is the system, right? So the two flat things are nothing but the phthalocyanines. So those two molecules, I don't know, will this work to show? Obviously no, I guess. Okay, that will not work because that is laser and maybe here it might work. Yeah, here it works. So you see here, so these two are the phthalocyanin units. These are simply organic molecules which are able to donate the electrons to the fullerene, and fullerene is the molecule that is an acceptor here. Okay, the picture is clear, right? So what we wanted to study in these kind of compounds is essentially when I shine the light, how quickly this charge transfer would occur. Okay, whether the charge transfer occurs or not is the first thing, how quickly that would be occurring is the second thing. So these are what are called as the charge transfer dynamics. Where these will be useful? These are useful in solar cells. When you wanted to study solar cells, you already know probably this normal concept, right? What will happen in the solar cells? Light from the sun is harvested, utilized. How are we doing that? light will come and somehow the whole system, here if you can think this whole system is nothing but donor plus acceptor combination, the complex. The entire complex will go to a excited state. In that excited state, there will be, after the excited state is done, that is what is called as an exciton, okay, and excitons will be formed, just for the namesake. After that, this bound electron hole pairs will be separated and they are separately stored. When you store them, there is again a potential is generated. That potential is the one that you would be utilizing at a later stage. For example, in your battery, if you are storing, you can use that battery to use your mobile phone, where again the electrons are flowing through the outer circuit. When you are touching that mobile phone, the electrons are going there and the loop is completed. So, solar energy harvesting is happening when the light is generating this electron hole pairs. For the generation of the electron hole pairs, somebody has to go to first excited state and then the electron hole pair has to be separated. So this kind of things needs the study of the charge transfer dynamics. Again, why we need to study? Because we need to identify the materials that can efficiently do this entire process. So the best examples that you guys might remember are the solar cells. Right, silicon solar cells. How many of you heard of silicon solar cells? Right, so whatever the rooftops generally that we are seeing, those are all made up of silicon solar cells. However, the issue with the silicon solar cells may not be the major issue, but one of the issues of the silicon solar cells is the degradation of those silicon solar cells is a big problem. Like any plastic material and other kinds of things, we are aware that they will be environmentally not very good. Similarly, if you wanted to degrade these solar cells, is it easy for us? It is not. Okay, silicon solar cells. So researchers are trying for other kinds of solar cells which can be degraded but should not be degraded immediately. Both are there, right? If you are a person who is purchasing the solar cell, you want your solar cell to be there for 30 years, if not possible for 100 years. Throughout your lifetime, you want the solar cell to be safe, right? But when it comes to the environmental perspective, what we want, the solar cell should be degraded provided I am giving some kind of impetus to it. Some push I will give so that it will be degraded, so that again earth will be benign. That's what we want. So such kind of possibilities will come from the organic solar cells. There are other things called perovskite solar cells, etc. Okay. So the problem with these organic solar cells, perovskite solar cells, is their efficiencies are not as huge as silicon solar cells. All of you are getting the point? You have a question? Huh.
Sir, why should it be degraded? Like, why do we want, you said it has to be degraded at a slower or like at some level?
You think like, so if you made a material, it is not degradable. That means you are going to keep it forever. Right? So, will that work forever? Definitely it is not. And you wanted to produce a newer material, newer thing, right? Like lithium ion batteries are there, for example, the mobile phones. After your mobile phone is dead, what you are doing? For you it is very simple, you will put it in your dustbin, or probably an electronic waste is there, you are giving to that person. Right? If you are doing that. But generally in India we don't do that much nicely. At least in abroad we have that kind of facilities where you have an electronic waste segregated, that electronic waste you are putting. But after that what will happen? You have to open the battery and you have to separate the materials that you used in order to prepare the battery. Same goes for the solar cell, same goes for the silicon solar cells or anything. Unless you are again removing each part and storing them in a separate manner, it cannot be reutilized. It is just dumping. You are going to a land, you are going to fill the land with these waste. So that means you are increasing the waste. That's not what it is, right? You wanted to have a sustainable future. Whenever you hear, are you guys hearing this word sustainability? Yes, this is now increasing more because people are realizing that it's not, you can mass produce probably silicon solar cells, but afterwards you cannot degrade them, you cannot reuse them. That is not a good idea. So when a plant is there, for us, think in this terms, plant is also harvesting the solar light. As long as it is there, it is useful. When it is not useful, it is dying and it is becoming a manure so that another plant can generate. Right? Or it is useful for some other kind of an animal on this earth. Some other life form it is getting converted to, which is important for us. We don't want to create waste. So the thing that is left by one of these organisms should be consumed by the other. Then only the life cycle will happen, right? Like you might have studied about these cycles in the environment, right? So this is also known to us even before the normal science. This is the word which we call as tyakta bhunjita in Sanskrit. If you are hearing this one, this was known very long ago. I'm not trying to make up anything here. These are there in our Upanishads. Okay. So what is tyakta bhunjita means? One is leaving it, the other one is eating it. Okay. So plants might be leaving the leaving the oxygen to us, and we are eating in one way or the other. Similarly, we are eating the fruits that plants are leaving. Whatever we are excreting, some other organisms are there that are taking that. Like this, the whole cycle, if you consider, that is this only one particular thing, that is tyakta bhunjita. So to answer your question, that's where the sustainability is important. So if a particular thing that you are man-made material is there, if it is feasible to degrade it, that is important for us. Okay. So in this context, one thing that we are dealing with is the charge transfer dynamics. Again, we wanted to understand, to identify the materials that can have the efficiencies that are close to that of the silicon solar cell. Okay, silicon is roughly having 33 or so percentage. The power conversion efficiency, the input power is like 100% if you are thinking from the sun's energy. The output right now is about 33%. That itself is very good. For which solar cells? Silicon solar cells. For organic solar cells, till very maybe like 6-7 years ago, the conversion rate is only 10%. Very recently, due to the advent of a new kind of materials, they went up to 20%. These are also called as non-fullerene acceptors. Okay, these are fullerene acceptors. If you are using non-fullerene acceptors, your efficiency can go up to 20%. Okay, so what our interest is to understand various kinds of other materials that can push this efficiency to even further. Again, as I said, the advantage with organic solar cells is you can destroy them at a later stage. That means they will environmentally, they are benign products. Second area that we are working is on this water pollutant degradation. Okay, what are some of the water pollutants? So this again goes back to the same question that he has asked. So here the specific compounds that we are looking at, there are several pollutants to the water. Okay, it's not one or two. We are focusing only on one of them. Okay, these are called as perfluoroalkyl substances. All of you remember alkanes from your chemistry. What is an alkane? It consists of carbon and hydrogen, right? C and H. So if you replace each of these hydrogen atoms and replacing them with fluorine atoms, these are what are called as the perfluoroalkyl substances. Also sometimes called as polyfluoroalkyl, because there are many alkyl substances there. So what are the uses of these perfluoroalkyl substances? Again, just telling you the story. I don't like if you guys are talking among yourselves. I want you to focus here. Okay. So what are the uses of the perfluoroalkyl substances? Perfluoroalkyl substances are the ones that you are seeing in your cooking pans. You have these pans, right? Non-stick ware is there. That's the one that the perfluoroalkyl substances are there. Firefighting foams. Fire is there. You are using these firefighting foams to stop it. Perfluoroalkyl substances are there. On the aeroplanes and other things, the paints that will be there, perfluoroalkyl substances are there, and various other places. What is the reason? The reason is the carbon-fluorine bond. Carbon-fluorine bond is one of the strongest bonds that can be there, because it is the strongest bond. When you put it to the fire, fire cannot simply break it, the fire will extinguish automatically. Because this is like that, you are putting it on the you are putting it on your non-stick pan, so that it is also having a oil repellent nature as well as water repellent nature. So you are using it so that you do not put that oil, but still you will make that dosa nicely. Okay. Same way for the paints, or on the other sides where aeroplane is going in the air, it's going at a very high altitude, at a very high speed. So there will be some abrasiveness, etc., that you don't want for your aeroplane to be there. So you kept this carbon fluorine bonds. So as such, these perfluoroalkyl substances are very useful. But since these are man-made materials, none of the biological enzymes are able to degrade them. So if you dump, for example, you did the firefighting foam, okay, after that will be slowly absorbed into the soil and that will never be degraded. And they are slowly coming into our water and we are drinking that water, or you are inhaling it through the air, and that is going and depositing in your kidney, in your brain, or in any of these other places, where again you have so many biological enzymes in your body, but none of them can degrade these substances because the carbon fluorine bond strength is very high and your enzymes are not evolved to degrade these things, because in the normal atmosphere they have seen so many kinds of bonds, but they never saw carbon fluorine bond. They might have seen nitrogen bond, so there is a corresponding enzyme called nitrogenase which can degrade that NN bond, but they never saw this CF bond earlier. Evolution never saw this, organisms never saw this CF bond, so they are not ready to break this bond as such. For that reason they are accumulated, and obviously they will create all kinds of problems to humans and other forms of life. So we need to find materials that can degrade these carbon fluorine bonds once you are using them and once your usage is stopped. That's one area that we are working on. Yeah, you had a question.
Sir, isn't the carbon fluorine bond highly hazardous?
That's what I'm trying to say. So it is useful as well as it has an issue. Useful because of the reasons as I said, like firefighting foams or non-stick cookware. She mentioned about clothes, paints, this one, that one. Wherever you don't want any degradation, this is very good.
But
And to the environment, this is very bad, because the moment you are putting it here, it will be staying it forever.
if we are using carbon fluorine bonds in non-stick pans, we may be consuming some amount.
That's what I'm trying to say. So as such, it will not be simply breaking. Okay, just because you are heating at 300 degrees centigrade, 300 Kelvin, it will not be degrading. Even if you are taking it to 100, 200 also, the carbon fluorine bond will not be degrading, because the bond dissociation energy of the carbon fluorine bond is very high. Okay, that's not the way it is. But the moment you will start using something, right, so you will be scraping it. After that, small parts will be coming out of that thin film that you have coated. That film you are consuming is a dangerous thing. Understood? Yeah. I will come to this part little later. So the other areas are catalysis, like you guys know about the use of the catalysis. How many of you heard of the preparation of ammonia Haber-Bosch synthesis? Okay, all of you know that. So we do need ammonia is one of the important things, because you see right now that the global population is continuously increasing, and for that you need the food. And food is coming because we are able to utilize the fertilizers. Earlier, this kind of a scenario was not there. That's the reason famines were very popular in the olden days. But right now we have a lot of fertilizer production. We should thank that Haber-Bosch process, because of which we are able to generate the fertilizers. Because you are generating the fertilizers, you are able to have lots and lots of food. So people are not dying from hunger due to the lack of food. Okay. Right now also people are under poverty, people do not eat food, all this is feasible, but that's because of the economical problems, not because there is no food on the planet. On the planet there is a lot of food thanks to the fertilizers. Okay. However, you want this particular process of fertilizer generation using the Haber-Bosch process is not very energy efficient. You want better ways to generate. So that's where you wanted to study other kinds of materials, other kinds of processes through which you can generate the ammonia. And that's one of the areas that we are also looking at. Okay, apart from the Haber-Bosch process, there are also other things like water gas shift reaction. Okay, so all these essentially require, right now I think there is a buzz for the hydrogen generation. How do you generate in general hydrogen? In order to form the ammonia also, you have nitrogen that you are sucking from the air, because air contains about 70% of the nitrogen. But hydrogen, where do you have the hydrogen? Water is there. But how are you generating the hydrogen? So in these in these Haber-Bosch processes, are you actually using the electrolysis to generate the hydrogen? What are you doing in order to generate the hydrogen? Did you guys get any opportunity to read that? From where we are getting the hydrogen for the Haber-Bosch process. In order to form the ammonia, you need N2, you need H2. N2, as I said, we are using some manners so that you can suck it from the air and you are using it. H2, you cannot get it directly from the air. Are you using the water in order to generate the hydrogen? Okay, what is it? How are we getting it? Water gas, do you mean steam as the water gas or something different? No. So actually what you are using is the petroleum products. Okay, that's why this is called as the grey hydrogen. Okay, there are like various forms, right? Green hydrogen, grey hydrogen, at least you might have heard. Blue hydrogen is like when you are getting it some other manner, etc. Okay, grey hydrogen is essentially when you are getting it from the petrol. So this is the way you are actually breaking this carbon hydrogen bonds that are there and you are generating the hydrogen and you are using that to form the ammonia. So these are again not so great processes because this consumes a lot of energy. So you want energy efficient process, that means you need to find alternate catalysts, and also you wanted to make ammonia in small forms. In the right now whatever we are dealing is for a very big reactor, okay, production in very high amounts. But can we have such kind of things for smaller units? Can you have not very big industries but small scale industries? Right now ammonia production require only large scale industries. Small scale industries turnover will be very less, but that will become a loss for the people who are founding that company. So alternatives are required. So one area that we were looking is plasma assisted ammonia synthesis. Okay, I think she has mentioned when she was mentioning about that. So plasma assisted ammonia synthesis is another area. So other thing is about the energy storage. If you remember for the case of charge transfer dynamics case, solar energy harvesting, you are breaking up this electron and hole, but you need to store that one also. How do you store? You guys already know. Where are you storing the energy generally? Batteries. Okay. So in order to improve these batteries, we need to find alternate materials that can provide you better energy storage devices. So these are the things, and additionally this new concept has come and we are working on how to use the quantum computers in order to study the chemical compounds. So quantum chemistry applications for quantum computers. What are quantum computers? How they are different from the classical computers? If you guys anybody know, please do let me know.
Classical computers would use bits, quantum computers use qubits,
And
where applying the principle of superposition. So you can assume any state between 0 and 1, any combination of states rather than just 0 or 1.
wonderful. So where did you learn this?
We had a
Okay, wonderful. By Professor Prabha Mandya?
Yeah.
Okay, cool. So we all are working together in all these ones. So you understood at least about that particular part. So once you have this really superposition, so that is only for a single one, not for everything, right? So when I am saying about the qubit is only one bit like type. But what we need also is in that same lecture, you might have heard also about the entanglement. Not yet. Okay. So what you need to also see is about how two qubits are interacting with each other, and not just two, you need many of such qubits in order to actually utilize the power of the quantum computer. Okay. So one of the first applications that you can do on a quantum computer is related to quantum chemistry. Again, if you know anything little bit about the Schrodinger equation, what you will be learning, I know that you guys know what is Schrodinger equation, but you might not have solved the Schrodinger equation as such, right? So what you will realize is you can solve the Schrodinger equation for a hydrogen atom. It is feasible. That means solve in the sense you can get an analytical solution for the Schrodinger equation. That means if I need the energy, I can write it in terms of a formula for Schrodinger equation. That's what you might be remembering right now. En is equals to some number you will get minus 13.6 electron volt by n square, or you might be returning in terms of n square h square, some other formulas you might have remembered. So those are feasible only for the hydrogen atom. If I ask you to tell me the formula of the energies of the orbitals in the helium atom, can you tell? The answer is no, you cannot solve it. So such kind of things you can get when you are going to the quantum computer. It should be in principle, it is not at this moment, but in principle once you have more than some 52 qubits or something like that, which are very less error prone. Tell me, no?
So I said that we can't solve it directly for helium, but if helium is made monoatomic,
It means monoelectronic.
Monoelectronic, that is true, but it is not helium anymore, right? That is helium plus, right? Discuss with me so that everybody will know rather than you two only will be knowing. Okay, so these kind of things like bigger molecules, etc., the solving their ground state energy is one of the interests to go through the quantum computing. Okay, so more or less these are the areas that our group is working on, and these are the people I wanted to just simply acknowledge before going to the original topic. So whatever I am going to discuss today, the work related to the energy storage devices is done by Mr. Subhadeep Banerjee. Yesterday you have seen here Kushbu, she is working on this organic photovoltaics. Just back to her, there is this guy, his name is Samir, he is working on this perfluoroalkyl substances. There are other people who are working in other areas, but we will not discuss any of those things today. Okay, I also want to thank these funding agencies that you are seeing on the top, SERB and the IIT Madras. If they are not providing me the funding, I cannot come and sit here and talk to you guys. Yeah.